Good morning. This is Exploring the Solar System Part 4 on exoplanets. So what are we doing? We're asking the question, why bother looking for planets that are going around stars other than the planets we know in our solar system? I'll be describing how we go about finding exoplanets and then finishing with a thought about looking for life. And I'll finish at the very last slide with where you can find more information if you're interested. So why look for exoplanets at all? Well, we can ask the question, is our solar system typical? We have a solar system with the sun at the center and 8 planets and a whole load of other rocks going around the sun. But the question is that typical of all the stars in the galaxy? Of the hundreds of billions of stars that are out there, would we expect to have any solar systems similar to our own? And if there are solar systems out there, if there are planets out there, are any of those planets like the Earth? Is there life elsewhere in the galaxy? Can we get an estimate of how many Earth-like planets are out there and whether there might be life out there? And ultimately, studying other solar systems around other stars may help us understand our own solar system. So how do we go about finding planets around other stars? Well, there are 5 methods. The first is described as radial velocity. That's looking for the wobble in a star produced by a planet orbiting the star. The second is transits, where a planet might move in front of a star and hence cast a shadow, effectively reducing the amount of light from the star. A third is direct imaging, which is rather tricky because planets are, generally speaking, many orders of magnitude fainter than stars. Then actually getting direct images of planets is rather tricky. The best we can hope for is to get a dot. If we can block out the light from the star, maybe we can see the much fainter planets. A fourth method is called microlensing. This is where we use gravitational lensing, the idea that any mass will bend light, and so we can use light from distant stars that are bent by a star and possibly a planet in the foreground. We'll see how that works in a little while. And the final method is called astrometry. In other words, measuring the position of a star, similar in a sense to the first, using the fact that a planet going around another star will cause that star to wobble. But in the first case, using the radial velocity, we work out the velocity of the star spectroscopically. In the final one, we again are looking for the wobble produced by a planet going around a star, but here we're hoping to find the actual wobble by the position of the star in the sky. Roughly speaking, these are in order of complexity. The first are relatively easy, the last are fiendishly difficult, but we'll see what each method actually is in just a second. So let's look at method number 1, the idea of radial velocity. This has been used to find more than 1,000 planets. If we think about a planet going around a star, then they actually orbit around their common center of gravity. So as the planet goes around the star is actually moving on a small circle as well, or a small ellipse. So the star will spend some of its time moving towards us and some of its time moving away from us. And so there will be a Doppler shift. As the star moves towards us, its light will be moved towards the blue end of the spectrum, and as it moves away, the light will move towards the red end of the spectrum. Not quite as simple as that little diagram would show. A slightly more realistic way of thinking of it is to think if that's the plan view on the left and the side view on the bottom left, you can see that the speed of the star towards or away from us is given by the sine wave oscillation that you can see in the top right. And if we think about the effect that has on the spectrum of the star, it doesn't necessarily make the star more blue or make the star more red, but it does mean that if we look at the spectrum of the star, if we see any absorption lines that correspond to particular elements in the star, we see those lines shift towards the blue end of the spectrum or shift towards the red end of the spectrum, back and forth and back and forth. So if we watch the spectrum from the star over a period of time and see what those absorption lines do, we can see them moving backwards and forwards if the star has a planet going around it, or perhaps more than one planet going around it. So it has the advantage that as it's a spectroscopic technique, and our spectroscopy can be a very accurate technique, we can see tiny changes in the velocity of a star. The actual speed changes that can be observed in a star are as small as a few centimeters per second. That's the sort of velocity that can be actually determined if you have a high-resolution spectroscopic system. Method number 2 is to look for transits, to look for planets moving in front of a star. So for this, we have to have the plane of the orbit of the planet effectively side on so that we see the planet move in front of the star. That then leads to a drop in light from the star, simply because we're effectively casting a shadow. If we think of the planet as simply being an object which absorbs all of the light that the star is emitting, then as the planet moves in front of the star, the light levels drop. So it's a very simple experiment. In principle, you don't attempt to resolve the planet, you simply look at the total amount of light coming from this star system and you record it, and if you see a dip, then you've got an indication of a planet moving in front of the sun or in front of the star. And the depth of the dip will depend on the area of the planet. So a large planet will cause a big dip, a small planet, a small dip. But if you think of the size of planets in the solar system compared to the size of our sun, it's only going to be a tiny change. It's only going to be perhaps a fraction of a percent. But because it can be done accurately, because we can measure the brightness of a star accurately, we can see even small planets moving in front of stars at some considerable distance. And as you can see, this has actually been used to find many thousands of planets over the last decade or two. We can see how it works if we follow what's happening for a multiple star system, such as here we've got a multiple planet system. If we have multiple planets going in front, here a large planet is going in front of the star, causing a big dip. And here we have a couple of smaller planets coming, and you can see what happens. You get a dip from one, and then if another planet transits, you get another dip. And so you can get quite complex structures in the dip of the star output. And for systems which contain 3 or 4 or 5 or 6 planets, you can get very complex results for the intensity of light, but we can figure out, as long as you see this happening enough times, as long as you can watch what happens over a period of ideally a few years, a few different transits, you can extract the information about multiple planets in a system. Ideally, it will be a very simple dip, but in practice, what you're actually doing is measuring the light from a star, so these blue dots represent actual measurements, and once you've got a whole load of measurements showing a dip, then generally speaking, that is fitted to what you would expect to see to get an indication of how deep that dip is and hence how large the planet is that's causing that drop in brightness. So that's a sort of representative indication of what you would expect to see. If we look at actual data, this is data from the James Webb Space Telescope. With a large mirror, you get much better statistics, and so you can see the starlight here relatively fixed in terms of its intensity, and then we see a drop as the planet transits the star, and then it picks up again on the other side. The larger the mirror, the more light you can collect, the longer you take data, the more accurate you can get this particular dip, and hence the more accurate the data is for the transit of a particular system. Method 3 is direct imaging, which is rather tough. Stars are very bright, but if you occult the star, in other words, if in your optical system you put in a disk which blocks out the light from the star, then it is possible to see a very faint planet which would otherwise be swamped by the light of the star. It can be done by occulting the star in the optical system, but as I'll say shortly, there are other plans for occulting the star by using an occulting disk not inside the telescope itself, but external to the telescope. This, as you can see here, has only been used to find a few hundred planets because it is a rather technically challenging thing to do. It has been done with Earth-based telescopes. Here we can see in past years, this is a time lapse taken over 12 years where the central star has been occulted, so the black circle in the middle is blocking the very bright light from the star, and over a period of a few years it's possible to see that this system has actually got at least 4 planets that are visible, the inner ones moving faster than the outer ones, because that's how it works. When you've got a stronger gravitational pull, the planets will move faster, just like Mercury moves faster than Venus, moves faster than the Earth, etc., in our solar system. So you can see this works best when you're looking down on top, as it were, on top of the plane of the orbits of the planets, but it will actually work if the planets are edge-on, which is a requirement for transits, but it will work for direct imaging as well. So here we can't see the planet, but then the planet shows once it gets far enough from the star, and then again, the X shows where the planet is. So you can see the planet is going round the star, and most of the starlight is being obscured by the central disk, but it's still possible to see a planet if it's large enough, if it's bright enough, even though that planetary system is orbiting the star edge on. And again, this is a time lapse taken over about 17 years of data, returning to the same star over and over again, taking snapshots and then making them into a movie. So this can be done. You do need to have a planet that's far enough away from its star that with an occulting disk you can still see the planet. It's always a trade-off between the sort of the artifacts that you can get when you try and block the star. You need the planet to be far enough away from the star that those artifacts are not going to get in your way. It's been done for many stellar systems. The James Webb Space Telescope is particularly well suited for looking at the formation of planetary disks and planetary systems around stars. It's up there at the L2 point, the Lagrangian 2 point above the Earth's atmosphere, so it doesn't suffer from any turbulence of the air in the atmosphere. It works in the infrared, and it has a very large mirror. So infrared is very useful because the dusty environments where planets are forming tend to glow well in the infrared, and this particular star called Fomalhaut is starting to show a system. We're not quite sure whether or not there are planets in the process of formation, but it's fairly clear that this is not just a homogeneous disk of dust surrounding this particular star. There appear to be quite definite zones. It's similar to our solar system in the sense that our solar system has got a few planets and an asteroid belt sitting out there beyond Mars, and also a Kuiper belt further out in the solar system, lots of icy objects. It looks like this system also has at least two belts, possibly being analogous to the asteroid belt and the Kuiper belt of our own solar system. Method number 4 is microlensing. A few planets have been found this way. Microlensing means the distortion produced by, here we see a distant star producing light and a star and a planet moving in the foreground. If we imagine that we are the blue dot at the bottom picking up light from the distant star, we can see that the starlight changes in intensity as indicated in the picture in the bottom right there. If I run that again, because it's only a short video, if I go back and run it again, as a star moves in front of a more distant star, it can actually focus by bending the light around it and so increase the intensity of light received at that particular point. And if the star that happens to be moving in front of the more distant star happens to have a planet around it, then you can see there in the bottom right that we might get a little blip. As the focusing effect of the star produces an increase in light, if that star happens to have a planet, then it can produce a small little blip on that curve, indicating that the star has got an associated planet, and multiple small blips would indicate multiple planets. This is actually being done, will be done by this spacecraft which is going up shortly, called the Nancy Grace Roman spacecraft, that is going to be looking for precisely this sort of effect of lensing from more distant systems, and one of its purposes is to use that microlensing to actually determine the existence of other planets around other stars. The final method for finding exoplanets is called astrometry, meaning measuring star positions. So just like earlier, I said that a planet going around a star will make the star wobble. Spectroscopically, we can see a Doppler shift, and we can do that very accurately. But astrometry is rather more demanding, and that involves simply looking for the star in the sky wobbling, even though that star will be moving by tiny amounts. And hence, to work out if a star is wobbling in the sky, you would need to measure its position relative to other stars to see those tiny changes. But that is precisely what the spacecraft Gaia has been designed to do. It's not looking for exoplanets per se, it's trying to map out the positions of as many stars in the Milky Way as possible. It's been doing that for some years. It's just about come to the end of its life now, but it has been measuring the positions to phenomenal accuracy of various stars in the galaxy And some of them are noted to be tracing out small circles. You've got to be careful because, of course, the Earth is going around the sun, and so you've got to be careful that you take into account the motions of the spacecraft itself. But when you've done all of that, you still find that some stars are moving in small ellipses or circles, indicating that they have planetary systems going around them. So not many planets have been found with this particular technique because it's a very demanding technique, but there is huge amounts of data now from Gaia, from many, many millions, if not billions of stars, and hence, by mining that data, we can find the existence of planets. When we do this, the most useful way of getting information out of what particular planet we're looking at is to use multiple techniques. I've shown you 5 different ways we can do it. In principle, you can use radial velocity to get the wobble. That depends on the mass of a star. And if we look at transits, remember that depends on the size of the planet as to how much light is blocked. If we use multiple techniques, we can combine them because radial velocity effectively tells us about the mass of a system. Transits tell us about the effectively cross-sectional area, so the size of a planet. And if we use 2 techniques and use those both on the same star system, on the same planetary system, then it's possible to extract information about the mass of a planet and its size. And of course, if we've got an estimate of the mass and the size of a planet, then we've got an estimate of its average density. And we know that if it's purely made of gas, we're going to have a relatively low density. If it's made of something like water, we know its density is going to be about 1 kilogram per decimeter. And if it was rocky or made of metal, then it would be higher densities. So we can estimate, bearing in mind that we have to think about the composition, because of course a gas giant won't be made purely of gas. A gas giant might have a metal core, for instance. So we have to think about how these things add together. But by getting an estimate of the density, and if spectroscopy can tell us a little bit about the atmosphere, which I'll come to in just a second, then putting all that information together, we've got an indication of the type of planet we're dealing with. Are we talking about a small rocky planet like the Earth? Are we talking about a larger planet like Neptune? Or are we talking about a huge planet like a gas giant like Jupiter? By combining information from different techniques, we can get a lot of information about what type of planet we're dealing with. And that's how we've come to the conclusion that we've got a mix of planets out there, including some that are very Earth-like and some that are very non-Earth-like. If we combine that with information about the temperature, we know how bright the star is that these planets are orbiting. If we know the surface temperature of the star, we can work out from the distance of the planet to the star, we can work out the nominal temperature, the equilibrium temperature of the planet around the star that it's orbiting. And that will tell us if we've got a small planet, for instance, are we talking about an ice world? Are we talking about a water world? Or if it's a rocky planet at a very high temperature, are we talking about a lava world? So we can determine, as long as we can get information from multiple sources, we can determine an awful lot about these planets, even though they might be, in principle, thousands of light years away. This is an indication of some of the planets we've found so far, the exoplanet zoo. This is not all of them, because we have something of order more than 5,000 planets that are known now. This is not all 5,000 of them. This is just 1,000, if you like, representative planets to give you an idea of the sort of variety of planets that have been found so far. These are on a horizontal scale of temperature, the nominal surface temperature calculated from, if we know the distance to the star and we know how hot the star is, we can calculate the equilibrium temperature. Cold on the left, you see minus 200 centigrade, very hot on the right. So you've got a rough scale there. Of course, if we're looking for some sort of a world in which liquid water exists, if we think that's important for looking for life, then we need to look in the Goldilocks zone, the zone where habitable planets might exist because liquid water might exist. And that is a relatively narrow part of this entire diagram. We can block off the left and the right because below that water will be frozen. Above that, water will only exist in the vapor phase. But there is the habitable Goldilocks zone that is just right for liquid water to coexist with solid water and gaseous water. Not surprisingly, if we look where Mars is, we find Mars is on the cold side, being a little bit further away from our sun than the Earth. And on the other side, Venus, which is a bit of a hellish planet with very high temperatures. Not surprisingly, Earth is relatively close to the middle of the habitable zone. These are equilibrium temperatures. This isn't the actual surface temperature of the Earth indicated here, because the Earth has an atmosphere, and that tends to raise the temperature of the Earth compared to what it would be if it was simply a bare body. If we look at what else is going on this, if we have a look in the bottom left-hand corner, we see some familiar items like Jupiter, Saturn, Uranus, and Neptune. There's the familiar planets of our solar system. So this exoplanet zoo does include our own planets just for reference, as it were, to give us an idea of how they fit in. If we look at some interesting exoplanets amongst this zoo, it's interesting to note that one of the closest happened to be Proxima b, which is only 4 light years from Earth. In other words, the closest star to Earth has a planetary system. 2 or 3 decades ago, we really didn't know how many star systems had planets. We didn't know whether our solar system was unique or whether a lot of solar systems, a lot of stars generated solar systems of planets. But now we know not only are there thousands of planets out there, but the closest one happens to be our immediate next door neighbor. What's the chances of that? This is another indication that probably planetary systems are everywhere. It's now estimated that at least half of all the stars in our galaxy, all 250 billion stars in our galaxy, have probably got planetary systems. It looks quite unlikely that stars develop without planets. One of the oldest ones found is this one up here, nicknamed Methuselah, which is found to be 12.7 billion years old. Bearing in mind that the universe is only 13.8 billion years old, that means this planet actually formed very early on after the Big Bang. Our own Earth is only about 4.5 billion years old, so that planet is significantly older by a factor of about 3 or so. So it looks like planets have been made going around stars as soon as there were stars. Stars formed perhaps a few 100 million years after the Big Bang. It looks like planets immediately followed. It's not like you have to wait a few billion years before the right conditions are set up to allow planets to form. Over on the right-hand side of this diagram, that's where the hot planets exist, generally hot simply because they are closer to their host star. The one in the top right there has a temperature of a rather balmy 4,000 Kelvin. It's rather difficult to imagine any planet with a surface temperature close to 4,000 Kelvin. It is presumably that temperature just because it is sitting only a few million kilometers or so from its host star. And the one in the very bottom right that you can see that looks a little bit distorted, that's a genuine rendition of what we think the planet looks like, because that one is only a few million kilometers from its star and is thought to be quite definitely egg-shaped. When we calculate the tidal forces that we would expect on this planet, it produces an egg-shaped result. So we are fairly sure that's what this particular planet looks like. There's a few more planets of interest in here. If we look at the one towards the top right, the rather darker color, we see that that is one of the largest ones we've seen. It is something like 10 times the size of Jupiter, but appears to be less massive from measuring the wobble of the star and what its effect is having on the star. It appears to be absolutely huge, but not very massive, which means its density must be really low. It's been calculated that the density of this planet is probably lower than the density of marshmallow. So quite what this planet looks like when you get close to it, we don't know, but it's significantly less than Jupiter. In terms of a name, well, the names tend to be fairly boring, like HAT-P-67b. That's a fairly boring name for any planet. But there's one in the top left here, which I think wins the competition for the most ridiculous name that they've come up with so far. Coconuts 2b is this particular planet. Coconuts stands for Cool Companions on Ultra-Wide Orbits. They deliberately looked for some planets that are orbiting a long way from the star. This one is orbiting 7,500 astronomical units from its host star. Remember, 1 astronomical unit is the distance from the Earth to the Sun. So in our solar system, this would be equivalent to a planet orbiting 7,500 times further away from the Sun than our own Earth. So our Earth takes 1 year to go round the sun. This particular planet would take something like 1 million years to go round its host star. And there are others. This Coconuts program is finding lots of solar systems where the planets are huge distances from their host star, as well as these hot things that we've seen on the right-hand side where the planets are very close to their host star. So it looks like solar systems come in all sorts of sizes, from those very close to those very distant from the host. And the final rather odd exoplanet in this particular zoo, I think, is this one. It goes under the ridiculous name of LHS1140b, but it's called an eyeball ocean or an eyeball planet because it's thought that this particular system, you can see it's fairly well over on the left-hand side. It's got a relatively low surface temperature, but its average temperature is fairly low, so it's thought to be probably ice. But it's close enough to its star that perhaps the bit of the planet that is closest to the star, it appears to be tidally locked, so it's not actually rotating. So one face of the planet always faces the star, and it's thought that that will actually melt the ice. So it's effectively an ice planet, except for the part that's facing the star, which could be liquid. So it could be liquid surrounded by ice. And so that's an artist's impression of what the planet might look like, and you can see why they've started calling these eyeball planets. That's purely an artist's impression, but they do have good evidence that makes them think that, yep, they could be either completely covered in ice or possibly covered in ice, but with part of the world an ocean. So it's interesting how much information you can get from all of these systems if you combine the information you've got from the 5 methods of observing exoplanets. Quite a number of different systems, telescopes or spacecraft, call them what you will. A number of these are giving us information about exoplanets. Gaia is designed to map stars, but because it can see stars wobbling, it also provides us information about exoplanets. The James Webb, part of its job is to look back in time to the very early universe to find out how stars came to be, how the very first stars formed. But along the way, because it's an infrared telescope with a large mirror, it's actually well suited for looking at exoplanet systems as well. It won't find exoplanet systems. It relies on other spacecraft to find the exoplanets, and then James Webb is told to follow up if there's anything particularly interesting worth looking at. But in addition to 2 spacecraft which are good at getting information about exoplanets, there are a whole host of spacecraft which are designed explicitly to find them. And here's some of them. Kepler went up quite a few years ago, and Kepler has found many thousands of planets by the transit method of looking at a particular chunk of sky. It's not looking at the entire sky, it's just looking at one small chunk of sky, measuring the brightness of those stars over and over and over again, looking for any of the stars that show a dip. And it's found 5,000 systems in which there are quite definitely planetary systems. And you can see there's more things coming online. There's an ESA mission in the top right there coming online in 2026. The Nancy Grace Roman telescope in the bottom there coming online in 2027. And this one in the bottom right is rather fanciful, this idea of following up anything we find in the next decade or so, following up to see if we can find more information about any worlds that are out there that are habitable in the sense of similar to Earth with similar conditions to Earth. And HWO stands for the Habitable Worlds Observatory. But that's not until perhaps 2040 or so. But one idea of looking for exoplanets, remember I said what you can do if you want to image them directly is basically stare at the star but block out the starlight and hopefully see any planets going around. You can do that within the telescope itself, but one thought is, would it be better to have the so-called occulting disk not inside the telescope, but why not have it outside the telescope? So there are plans, they haven't quite decided how to do this yet, but there are plans to have a telescope with an occulting disk which is separate from it. So the occulting disk will unwrap itself and unfold itself into something about 100 meters or so across, and then with small jets it will fly something like 50,000 kilometers away from the telescope, and it will be programmed to sit in front of a star, and it will block out the light from the star itself, as indicated by this animation, And if you block out the light from the star, then it's hoped that you'll be able to see in more detail any planets that are going around that star. It has this sunflower design to try and minimize the effects of diffraction. There will always be diffraction when light passes a circular occulting disk like this, but if you just had a perfect circle, then the diffraction pattern would be a load of circular rings, and if you're trying to see planets going around the star, the last thing you want is a whole load of circular rings. So having this petal shape will still produce diffraction effects, but the diffraction effects will take the light and spread it over the entire region around the star rather than concentrate it in rings around the star where you may block the apparent position of planets. So this star shade concept is still a concept, but they are building in the lab simulations, if you like, or tests of can you actually get mylar foil or something like that to wrap up really small so that you can fit it into the top of a rocket, and yet it will unfold on its own to something 100 meters or so in diameter. Similar sort of technology required to the sun shield of the James Webb Space Telescope, but there are ways of doing the origami such that something that large can unfold into from something that's only the size of a barrel or something like that. So how do we go about looking for life if we think there are planets out there? Well, there's a number of things we can do, because when we're looking at transits, the planet may transit in front of the star or be eclipsed behind the star. So as it goes around, we have two ways of actually getting information about the composition of the planet. As the planet goes in front of the star, then we can look at the star light that's coming through the atmosphere of a planet, because it's not simply being blocked. We would expect that the atmosphere of the planet, when it goes into transit in front of the star, some wavelengths might be effectively absorbed by the atmosphere. The atmosphere might be quite thin, like it is on the Earth, for instance. So again, it's going to be a very small effect, but some wavelengths might be absorbed more by the atmosphere than other wavelengths. And hence, if we look at that dip in different wavelengths rather than just integrating the total light from the star, we might see a difference in the depth of that dip according to particular wavelengths which are absorbed. In principle, we could also do spectroscopy on the other side by looking at the total light, which is from the star and the planet, before and after it goes into eclipse. Just before it goes into eclipse, the total amount of light we're receiving is the light from the star and the light from the planet. But when the planet goes into eclipse, we're only picking up the light from the star, as we're no longer seeing the planet. So if we look at differences in the spectrum just before and after the planet goes into eclipse, we can see changes in the spectrum which are the result of the light from the planet, not the light from the star. So there's two bites of the cherry, as it were, to get information from spectroscopy about what particular wavelengths are present because of the planet rather than because of the star. And if this is done, again, with enough signal to noise, you're looking at tiny differences between spectra, so you need good signal to noise. Hence, this works really well with a very large mirror like the James Webb. Here at the top, we see a transit where the light from the star has dipped, but if we look in more detail at what's going on at the bottom of the dip, we find at different wavelengths, we get different depths of the dip. We still have to worry about signal to noise. We need an awful lot of data here, but you can see that at some wavelengths it dips by this much, whereas at other wavelengths it dips by just a little bit more. So we can deduce, if we look at the transit at lots of different wavelengths, we can start to build up a spectrum of which particular wavelengths are being absorbed by the atmosphere of this particular planet. And that's been done for a few different systems, and we are still dealing with a rather ropey set of signal to noise. We need more data, we need better data. Ideally, we want bigger telescope mirrors up there. But at the moment, the James Webb is capable of taking data at lots of different wavelengths. And then here we've got the data as white dots, and then it does a fit in blue, assuming that a number of different molecules are present in the atmosphere. What's the best fit we can find of the data which is consistent with this set? And we deduce the existence of some sodium, some water, some carbon monoxide, in this case some sulfur dioxide. Occasionally you see carbon monoxide as well as carbon dioxide, sometimes you see dimethyl sulfide. There are lots of different molecules which have been found in the atmospheres of exoplanets, even exoplanets hundreds or thousands of light years away. The fact that we can determine the chemical composition of an atmosphere of a planet going around a sun somewhere else in the galaxy is truly phenomenal in terms of how well the James Webb Space Telescope is actually performing. So just to summarize where we're at, we've been finding exoplanets for about 30 years now. The first one was found in the early 90s, but it was very slow to get off the ground, if you'll excuse the pun. So this is a diagram of what planets have been found, mapped out with their orbital period on the horizontal axis and how massive the planet is relative to the mass of Jupiter on the vertical axis. And here's a few solar system planets dotted around just for context. There's Jupiter and Saturn on the right, Uranus and Neptune, and on the bottom left here, we've got Earth and Venus. So we haven't got all the planets mapped out, but it's just an indication. If I now run from 1992 forward, you'll see what planets have been found year by year by year. To start with, very few. But then, as we turn through the millennium, we start to get lots of different data, and eventually the Kepler spacecraft starts to use the transit method to find lots of different ones. They are coming up now in purple, and as Kepler stares at the sky year by year, we suddenly find more and more and more exoplanets via the transit method. And you can see there are, in fact, lots of discovery methods other than the main 5 that I've been talking about. So now this is almost up to date. This is 2024, and you can see that we now know of thousands of different exoplanets found by lots of different methods, and we can start to do statistical analysis. It's clear that they're not randomly scattered through this particular scatter plot. There appear to be bunches. There seems to be a bunch in the top left, a bunch in the bottom left, and maybe a bunch in the top there. This is partly observational bias, because if we're looking, for instance, to see the wobble of a star, we are going to preferentially find those systems which have a large planet which is producing a large wobble of the star. It's going to be very difficult to find small planets. The same for transits. If we're thinking about a planet blocking the light from a star, big planets are going to be easier to see because they block more light. Tiny planets, smaller than the Earth, are going to be difficult to see because they only block a very small amount of light. And therefore, there is going to be bias in these statistics. This is not necessarily representative of all exoplanets that are out there. This is representative of the planets that are easy for us to find. Maybe later spacecraft will actually extend this. But you can see that at the moment, there aren't many around the Earth-size, Earth orbit sort of position. There aren't actually many around Jupiter. Most of the planets that are the mass of Jupiter appear to be much closer to the Sun with much shorter orbital periods, so-called hot Jupiters, because unlike our ice giant, they may be a similar size, but they're much closer to their host star and are generally much hotter. So there's still a lot of work to be done to try and decide what the actual population of exoplanets is, based on the fact that we have always observational bias by any technique that we use, whether it's transit method or the radial velocity wobble method or any of the others. There will always be bias in the statistics. But it's still amazing to see over the years just how many thousands of planets we now know exist. So if you're interested to know more, NASA have a directory in which they give information about every planet that they've found. There are archives there. There's the Caltech archive as well as the NASA dashboard. And there are 3 interesting systems coming online, 2 very soon, an ESA mission and a NASA mission, and 1 for the long distant future, which who knows, I might not be alive for, but sometime beyond 2040, there'll be interesting developments beyond the NASA and ESA spacecraft that are going up very shortly. Thank you for listening.